Hello, I'm Walker Khan, and this is Lab 4, Circuits and Capacitors. The purpose of this lab is to utilize simulated voltmeters and ammeters to measure potential difference in conventional currents. We can achieve this by applying Kirchhoff's loop rule and node rule, alongside Ohm's law, to mathematically understand the phenomena within resistors and capacitors. To elaborate, Kirchhoff's loop rule states that all electric potential differences should sum up to zero. The node rule states that all currents flowing into a node equal the sum of all currents leaving it, the conservation of currents. Some other principles include knowing the behavior of capacitors and the conservation of energy, which links back to the loop rule. The series circuit on the right utilizes two 1.5 volt batteries alongside 147 ohm resistors. Based on Ohm's law, I calculated the current to be 0.02 amps, which lines up with the ammeter reading on the simulation. In the instance where an ammeter is placed backwards, I read the current to be negative 0.02 amps. When asked to find the potential difference at the place of an ammeter, I found it to be 3 volts. An important note to state here is that the black wire is connected to batteries with a combined potential of 3 volt, whereas the red wire is experiencing 0 volt. In terms of the ammeter, it reads 0 amps because our system is not a closed circuit, thus no current flow. However, this follows the assumption that the voltmeter has infinite resistance in our simulation. Following the graphic seen on the bottom right, I recorded the potential difference on specified regions into the table on the left. When you add all of these values up, we find the sum to equal 0 volts, thus abiding by the loop rule and the conservation of energy. The graph on the top right shows the relationship between the potential and position based on the table. For this part, we wanted to add an ammeter in parallel. As seen on the right, an ammeter is in parallel with a 100 ohm resistor. Both ammeters now read 0.06 instead of 0.02 because of the node rule, which indicates that the current is split between the 100 ohm resistor and the quote-unquote 0 ohm ammeter. The current prefers to take the path of least resistance, thus strengthening the current flow within our circuit. Knowing the potential differences in some regions, we can calculate their resistance. The results are as shown on screen. The wire and ammeter contain 0 resistance because they hold no potential differences within this ideal simulation. Now we want to observe charging capacitors. In the following circuit model on the left, bulb starts at its brightest and gradually dims as the capacitor polarizes, in other words, charging the capacitor. When removing the battery from the circuit, the capacitor discharges. During this process, the light bulb once again is at its brightest and gradually dims, though this time the current is flowing in the opposite direction due to the orientation of the charges. Shown here are the charge and discharge times for a 10 and 20 ohm light bulb. We can see the times of a 20 ohm bulb almost double that of the 10 ohm counterpart. In other words, we double the resistance within a circuit, the charge and discharge times approximately doubles. For this part, we want to graph the relationship between discharging capacitor time and voltage over a 20-second interval. More specifically, we want to graph the natural log of the instantaneous potential difference on the capacitor divided by the initial potential difference against time. The slope on the trend line will help us in calculating the RC value. What is seen on the top is the potential difference formula that justifies the use on the natural log of V over V naught seen previously. We find that the value is equivalent to the inverse of our RC value multiplied by -1 in time. When setting our slope equal to -1 over RC, we finally find that our RC value itself is equal to 7.102 seconds. What if we use a real ammeter for this lab instead of a simulated one? How will that affect our data? A real ammeter will have a small amount of resistance, meaning that it will slightly inhibit current flow. As a result, overall current readings will be less than what simulated data would show. Now, what if we use a real battery to charge a real capacitor without a resistor? How will that affect the rate at which the capacitor charges? In an ideal scenario, the capacitor reaches full charge instantly since there is no resistance within the circuit. However, in real life, all circuit components have some level of resistance, even if they were a battery and capacitor. As a result, the capacitor will take some time to charge. Thanks for watching.